So far what we have done is, well, choose pole locations and these pole locations has provided us with the state feedback matrix K using the command place in Matlab. So what we'll do now is something different. We'll work with a control cost J, which is an integral of the following quantity. Okay, and well, this is really optimal control design, and there are two main objectives. Make sure, and this is the role of this one, that x of t, well, is small and converges to the origin as fast as possible, right? And the other objective is to make sure that the input, the control signal, is small in order to limit the actuator effort. And of course these are conflicting objectives, because if you want to make xt small as fast as possible, there is a chance that the control will be nervous and that this will increase u of t. But what is important is that you see here that we work with not pole locations, but with two matrices Q and R, and that given Q and R, you obtain the state feedback matrix. And the reason we look for another method is that, well, it's not always easy to translate specifications, such as overshoot, settling time, rise time, and so forth, in desired pole locations, especially for complex systems. Remember also that in MIMO systems we have seen that the matrix K, right, offers some freedom because there are n times m parameters in K and there is only n eigenvalues to assign. Okay, so there is some degree of freedom there. And so the question is, what is the best K among all the possible K for a given pole configuration? Well, optimal control design provides a solution for those difficulties. Here we make a small link with the course on linear algebra, where we have seen the concept of a positive definite matrix M. A positive definite matrix M is a matrix that is such that X transpose MX is larger than 0 for all X in Rn, right? M here is an n by n symmetric matrix, right? And we have a closely related definition with positive definite replaced by non-negative definite, and obviously this one is going to be replaced by greater or equal, right? And we have seen that a symmetric matrix is positive definite if all its eigenvalues are positive. We had also seen that it's possible to work with elimination, and well, then you have a very similar theorem which says that a symmetric matrix is positive definite if all its pivots are positive. And actually, to test if a matrix is positive definite, it's probably easier to use elimination and to test if the pivots are positive. So this is the LQR. Okay, you see here Q is the Q that you see over here, and the R is the R that you see over here. Another way to say, and the L is for linear, is linear quadratic regulation. Okay, so the system we're working with is in state space format, as always in this course, and in here we simply have taken d is equal to 0, so there is no direct feed-through term. But as you know, in practice there will be hardly ever a case where you have a direct feed-through term. So the performance criterion that we're using is an integral from 0 to infinity of this quantity over here. And you see that there are two terms, one that penalizes the state. You want the state to go to 0 as fast as possible, and the other term is a penalty on the control energy, right? The matrix Q over here is non-negative definite, which means that this term here is larger or equal to 0 for x positive, and this one is, well, since r is positive definite, larger than 0 for u positive. So we really want to impose a penalty for any u that is positive. So what is the idea behind the cost that is shown over here? Well, I've taken this slide from a Matlab video course. This is part 4, what is LQR control. So you can have a look. There are other parts also really dedicated to other topics of state space control. But as said over here, and as we have said before, this term over here is really penalizing bad performance, and we want the state to go to 0 as fast as possible. Here you have the evolution of the state with respect to time. So you have two situations here in blue and in brown, and clearly in brown the state goes to 0 faster, so you have better performance. What is shown below the line is really what we integrate from 0 to infinity, right? What we do not want, of course, is negative values, and this is why we work with quadratic functions, and this is why we have this matrix Q here, which is non-negative definite. Okay, so that this is always, well, positive or 0. This one will even be positive. Okay, remember that this is the term in which we penalize the actuator effort, and of course we have this compromise, as we will see later in the course. Well, for your information, the optimal control that minimizes the control cost that we have defined previously is a linear state feedback law of the type given here. So it's the same type of equation as before. You can even add a feed forward part nr, and the n is computed as previously. So for n, it doesn't matter if k is obtained using pole placement or optimal control. And this k is computed from the solution of a so-called algebraic Riccati equation, and under reasonable assumptions there will be a solution to this matrix equation, right? And furthermore, the state feedback that would result, so the matrix K, will ensure that the closed loop system is stable, so that the eigenvalues of a minus bk are all in the left half plane. You can use linear quadratic regulation LQR control without a surprise in Matlab using the command LQR. Matrix Q that penalizes the state, and the matrix R which penalizes the control energy, are respectively non-negative definite and positive definite, and they are tuning parameters for DLQR control problem. So one particular choice of Q and R is interested, and it might help you to understand what happens. Well, the first one is Q is C transpose C. Remember that C is the output matrix, and R is equal to lambda times the identity matrix. So if you plug this in X transpose Q, which is C transpose C now, X, this will produce this quantity here. So we are penalizing the output, and because R is lambda the identity matrix, well, U transpose R U becomes as follows. So here it's the control energy, and here it's the output energy, and you can quite easily see that lambda here, well, kind of allows you to make a trade-off. If lambda is small, okay, this means that you can use a high control gain, aggressive control, and you would expect faster convergence of y to 0. If lambda is large, well, then you expect low gain control, and the response will be more sluggish, slower, okay, because the commands that you're allowed to use cannot be as nervous as aggressive. The Q and R that we have proposed earlier, so Q is equal to C transpose C and R is equal to lambda I, might not be the best choices for an LQR design. In practice, choice of Q and R is very difficult. So this is why if you're trying out LQR design, well, you might test Bryson's rule, right? And Bryson says, well, you should use the following matrices Q and R, where the xi max and uj max are the largest desired response or control input for that component of the state or actuator signal. Often additional relative normalizations are added on the various components of the state or control, and these are this alpha I and beta I that you see over here. You see also that there is this parameter rho, and rho is used as a relative weighting between the control and the state influences. This is, well, more or less equivalent to the lambda that we had introduced before. So what we have done previously is use a law. U of t is n r of t. R of t is the reference or set point minus k x of t, where x of t is the state. We have seen previously that, well, using this control law, we can achieve a zero steady state error, but that it is not really a robust way to do things, because in reality you'll have a model that will not be an exact copy of the system, so the n that is computed will not lead you to a zero steady state error. So this is why we wish to work with a feedback law with integral action. So here you have the standard state feedback, right? And we have added here a term minus ki xi, where xi is the integral of the outputs that are being controlled minus the set points, okay? And this second term is really implementing the integral action. So if you take the derivative of this equation, obviously you obtain the following equation, and this equation will be used in the next slide when we extend the state. So these are the two original equations that come from the state space description. We are implementing this law over here, where xi of t is the integral from 0 to t of y of t minus r of t dt. So if we take the derivative, this is the equation that we obtain, and y you can write in terms of the state, so it's Cx, where C is the output matrix, minus R. So what we'll do now is construct an extended state, right? And it will be X with below the state xi that comes from this equation over here. So remember that in reality the system might be multivariable, so there might be several components in R and several components in Y. Okay, remember the process of the 3-tank system. We were controlling the height in tank number 1 and tank number 2, so R and Y were vectors, right? So how are we going to construct this extended model? That's quite easy to see. Everything that is above the dashed line implements the original system. X dot is ax plus bu, there's no dependence on R. And if you look at this equation here, okay, xi dot is cx, this is what you've got over here. There's no dependence on xi, there is no dependence on u minus r, so I need an minus identity matrix over here, and the output only depends on x, so this is the extended state model. So what we can do now is use this to design a feedback law based on this extended state model. So the feedback law will be minus k extended times the extended state. Okay, so this will be k extended, and for that you can use pole placement or you can use LQR design. In summary, integral action can be easily implemented using the following extended system with the matrices defined as follows. So you design a state feedback for this extended system using either pole placement or LQR, and you then have to split the state into original state X and the one that is coming from the integral action, right? And K is split likewise. We had this discussion about different C's. Well, the C that you have to use over here is the C that was also used previously in the design. U is NR minus KX. Okay, so here we're doing differently, but we were using it in C there. Well, this is the C that we're using here also. It's the C that selects the outputs for which there is a set point. Note that the equation that is implemented is u of t minus kx of t minus ki xi of t, and remember that xi of t is the integral from 0 to t of y of t minus r of t, right? And the whole thing is integrated with respect to t. So if you plug this one in, you can rewrite this as u of t is equal to minus kx of t plus ki times, well, the integral from 0 to t of rt minus yt dt. Okay, so this is why you have a plus over here, and that you have the standard way of seeing things. It's set point or reference minus the signal that you're controlling, and this is producing the standard control error, which is r minus y. So you can see here in gray that what you see is the linear system with realization A, B, C that has been used to design K and ky. In reality, of course, what you will see in the box is the actual system, and in reality the actual system will of course be non-linear very often. So we should maybe replace this box by something that looks like this. U goes in, Y comes out, and the state comes out, right? In this way we do not see what's happening inside, because as I said, very often this will be a non-linear system. Well, so far we have talked only about continuous time design, and of course what we'll have to do is take our control design and also our observer design and implement it on a processor using a sampling period TS. Okay, so the idea is that we first do a continuous time design, okay, because, well, for pole placement, for instance, well, the link between the performance specification and the pole locations is so much better understood in continuous time. So once we have this continuous time design, what we'll do is take the pole locations and transform them in pole locations in the Z plane, right? And then what we'll do is use a realization of the discretized system using the ZOH method, because we want to take into account the zero order hold in our design, and this will then produce a K that we can use on our processor. One way to work would be to obtain a discrete time realization of the system AD, BD, CD, right, using the ZOH discretization method, and then assign the poles in the complex Z plane. The subscript D here means that we are doing things, well, in the discrete time world. Okay, we will see in the teaching unit digital control that it is also possible to obtain a region of good performance in the Z plane. Okay, this region of good performance will of course be inside the unit circle, and it will be the intersection of three zones: one that is asking for a small rise time, another one that is asking for a small overshoot, and another one that is asking for a settling time that is small. Okay, and as you can see, well, assigning the poles in discrete time does not come as naturally. So what we'll do is do a continuous time design. So we'll assign continuous time poles as explained before, and the subscript C means here poles that were assigned in continuous time, and we'll use the relation between the Z domain and the S domain. Remember that this relation is Z is equal to exponential TSS, and TS is here the sampling period. Well, if you now have those poles from a continuous time design, you can translate them to poles that you can then use in a discrete time design together with the discrete realization of the system obtained using the ZOH discretization method. We have seen that it's easy to obtain a discrete time realization of the original realization using, well, the ZOH discretization method, and for that you can use a Matlab's command C to D. If you use it without arguments, you will automatically be selecting the ZOH discretization method. So remember that our open loop state equation is x of k plus 1 is AD xk plus BD u of k. We'll implement a law that is exactly the same as previously. It is again a static control law. So u will be, let's say u of k is n of r. R is the reference or set point, as you like. Rk minus k times the state in k. So if you inject that in the previous equation over here, this is what you obtain, and we have now a state equation in discrete time that is AD minus BD k. Okay, and this is how this can be represented. Here you see the control law. uk is n acting on rk minus k acting on the state, and here you have the linear system. You see here xk plus 1 is bd acting on u plus ad acting on xk, and to go from xk minus 1 to xk you have the delay operator. The comment that I made about, well, here a linear system is still valid. In practice you will have a non-linear system, so here a representation with uk yk and the state xk coming out would probably be better. Well, note that we can go to the z domain by using the z transform. If we do this, we'll have z x of z is equal to ad minus bd k x of z plus bd n r of z. So if you reorganize things, you can write this as zi minus ad minus bd k, right? xz is equal to bd n rz. So you can obtain xz by using the inverse of that, and if we inject that in the output equation, we have the relation yz is equal to cd zi minus ad minus bd k inverse bd n r of z, and this is really the closed loop transfer matrix. Well, we have just obtained the closed loop transfer matrix, and we can obtain the steady state response using this equation over here. And what we have over here is the static gain matrix. That's the relation between the reference signal here in steady state and the output in steady state. And now of course we have to consider this transfer matrix, closed loop transfer matrix in z is equal to 1. When we were working in continuous time in the Laplace domain, we had to consider s is equal to 0, but remember that we have this relation between the z and the Laplace variable, so s, that is 0, corresponds to indeed z is equal to 1. In steady state, of course, well, we want the output to follow the reference signal, so this must be here a matrix that is an identity matrix. If we compute this static gain matrix, we have to replace z by 1 over here, and we obtain this matrix that we can now equate to an identity matrix. So we need to solve the following equation, and if you do this, it's not really difficult. We simply have to multiply by the inverse of this matrix. We obtain the matrix N. And of course, this feed-forward gain is different in discrete time because we have to use the matrices AD, BD, and CD, but also the formula is different, right? In continuous time, we had S is equal to 0, and here we have Z is equal to 1, so there is a difference over here, so beware not to make this mistake when you implement your feed-forward gain in discrete time. In the single input, single output case, we have here one input, so B has this form, one input and one output, right? So this here is a scalar. So the feed-forward gain now becomes a scalar. We cannot call it n because n is the number of states, right? So we'll call it nr to make the link with the reference or set point signal. Well, let us come back to this relation and let us have a look at it in the case of a unit step response, right? Remember again that R is in Rm. That hasn't changed. We have m actuators, so we can only control m variables. In this case here, if we are in the z domain, since we have a number of unit steps, we'll have a vector here with a number of times z over z minus 1. This is the z transform of a unit step in discrete time, right? So the steady state value here is also a vector in Rm, of course, and it's the limit when k is tending to infinity of y of k. We can use the final value theorem in discrete time, so it's a limit when z is tending to 1 of z minus 1 y of z, right? And y of z in this case is, well, the closed loop transfer matrix times this set point signal. So we have limit when z is tending to 1 of z minus 1, the closed loop transfer matrix, right? And this one will rewrite it differently. We'll rewrite it like this, and here we have this vector composed of m ones in the vector, right? This one and this one will cancel out, and what we'll have here is the closed loop transfer matrix evaluated in z is equal to 1 times this vector over here composed of ones, right? But this is the steady state value of the reference signal. Of course, if you use a unit step in steady state, what you have is a 1, of course. What you expect here for the steady state output is, of course, also 1s. We expect the output to follow, so indeed this must be an identity matrix. So here's a summary of the method in discrete time. Well, you take the poles of your continuous design and you translate them to specifications on the poles for discrete time design using this relation over here. Once you have obtained a state space description in discrete time, and you can obtain it using the command C to D, right? You're using the ZOH discretization method. You can compute the state feedback gain matrix K using Matlab's command place. Place will use the realization ADBD and the discrete time pole locations. Once you have the state feedback gain matrix K, you can now compute the feedforward gain matrix using the following formula over here. And again, because this is a sort of mistakes, this formula is different than the one that we had for continuous time design. So you can of course implement integral action also in discrete time, and as before we have to construct an extended state model in which we are going to, well, construct an extended state X of E. Well, the first part will be the state of the original system, and the other part of the state will be the states associated to the integral action. So what we have to do is use a discrete time state space representation of the system, and these are the two equations that I've shown, and I need to add a discrete time equivalent of xi dot is equal to y of t minus r of t, right? And this is really representing an integrator. In discrete time, you can obtain the integrator as follows. So now you'll have k over here, and this will be y of k minus r of k, and assume that you've computed the integral of this signal up to time kts, right? So you have obtained this thing here, and that you need to obtain the output of the integral in time k plus 1 ts. So this is ts. So what we need to add is the area under the curve in between kts and k plus 1 ts, and what we'll do is approximate it by this area over here. So this leads us to the equation. Output of the integral in k plus 1 is the output of the integrator at k, and this is what I've shown here. The area under the curve up to kts, and you have to add ts, right? This is the width of this element here, and then we have to take the height, which is really yk minus rk. So this is how you end up with the integral, or the equation for the integrator, right? So as I've said, now you can construct the extended state model. Here you have the extended state, right? Above everything that is dashed here, you have the original state equation, and below, well, you can construct the extended state model from the equation that is over here. So xik plus 1, it's xik, so this is this one here. You have tsyk, but yk, you see it over here, it's cd times xk. So this is really ts times cd times xk. So this will lead to this term over here. There's no influence of the input, and there is an influence of the reference. So this explains the minus ti over here. Okay, and the output equation is really easy to obtain. So what we'll do is design a state feedback law, and again, it doesn't matter how you obtain this feedback law. You can use pole placement, you can use LQR, but in discrete time design, as we will see just after these few slides. But once you have it, well, you can use it for integral action, and as before, what we'll do is split the state in two according to xk and xik, and this will produce the state feedback k and the ki that you're going to use in the integral action. So here's a summary. Here's the extended state space description of the system for integral action with the matrices A, E, B, E, and C, E that are given over here. Again, because this is leading to many mistakes in the control lab, these extended matrices A, E, B, E, C, E are different to the ones that are used for continuous time design. So when you implement integral action in a discrete time, pay attention not just to copy what you did for continuous time design, because the matrices are different. You can see it already here. There is of course a dependence on TS. Once you have this extended state space representation, you can design a state feedback for it over here, using the method that you like, pole placement or discrete LQR, and then splitting the state in original state and integral state, you can obtain K and Ki, and these will be used in the implementation, as we will show next. The picture that you see here for discrete time implementation of integral action looks a lot like the one that you had for continuous time implementation, except of course that the Ki, right, and the K come from a discrete time design. Also, the integrator has now to be implemented in discrete time. So there are different ways to do this, and I refer to the course of digital control. The best way to implement the integrator, and you'll do this probably in Matlab Simulink, is to take a discrete time implementation of the integrator using a trapezoidal approximation, and this is really an integrator with transfer function ts over 2 z plus 1 over z minus 1. Right? If you select a discrete time integrator in Simulink, there is a menu where you can choose the approximation in the discretization and choose trapezoidal. It is of course possible to implement a discrete time LQR design, a discrete linear quadratic regulator, and without a surprise, the Matlab command is DLQR, right? You start from a discrete time state space description of the system obtained after discretization of the original system with the ZOH method to take into account the effect of the zero order holds. The design is based on a performance criterion as before, and the only difference is that the integral now becomes a sum. Q and R, the tuning matrices, have the same meaning as before. And for your information, well, the state feedback law is as follows, with K constructed from the solution of a discrete algebraic Riccati equation. So here you find an example in Matlab, and it's an example that I've drawn from the book of Franklin and Powell. As you can see, it's a system with one input and one output, and it has 5 states. You can see that there is a pole placement design and an LQR design. So in first instance, we're working in continuous time, right? So here we do the pole placement. So you need to select 5 poles, and this will be the exercise that you'll have for your particular process. How do you choose those poles? This has been discussed in the course, but once you have the poles, you can use the command place to obtain the state feedback matrix, right? This is this equation over here, and once you have the state feedback, you can compute the feed-forward gain n as shown in the course. Once you have your control, and your control is minus k1x here plus nclp r, well, what you will do in your control laboratory is implement this control law on your model in Simulink. But here it's an example where everything is done in Matlab. So what is done here is compute the closed loop state realization. It's clearly seen over here. And then what you can do is construct the transfer matrix, or transfer function in this case, because it's a scissor system, from R to Y, and here from R to U. Okay, you can see here that the output matrix will be minus k1. This is clearly seen here, and the direct feed through is nclp. This allows you, well, to have a look at a step response, have the influence on Y. Here it's not Y, but it's U, of course, and also to look at the control energy. You should never look at a design without having a look at the control energy. Well, you can also do LQR design, and here we have chosen this approach where Q is C transpose C, and where R is, well, lambda times the identity matrix. Since we have only one input, R is really lambda. So here the lambda is 1, and then you simply use the command LQR to obtain the state feedback. For the rest, everything stays the same. You now compute the feed-forward gain based on, well, K2, right? Because ACLP enters over here. Here the feed-forward gain was computed using this matrix here, right? And it was depending on K1. So you see there is no really a major difference between pole placement and LQR, except that here, of course, you choose the poles to influence your shaping of the response, and here you choose tuning matrices. But once you have the state feedback, everything remains the same. And what you can do now again is look at the step responses, as I said, from R to Y and R to U. Well, as discussed before, there is an alternative for the command place. You can also use Acker, right? Well, Acker will only work for CISO systems. Okay, and remember also that it's not that numerically reliable. If the number of states grows typically above 10, then you can expect, well, numerical problems. Well, the downside of place is that you cannot place multiple poles. Remember that, well, if you have multiple poles, then you have these Jordan forms, okay, and this is why you can expect problems. So place, you can only place single poles, so this means that all the poles that you use over here must be different. Okay, so you cannot, for instance, place poles in -1, -1, and then -2, right? This is impossible because these are multiple poles. Well, of course, I then see students that say, well, I'll place one in -1 and the other in -1.0001. Well, I agree with you that the poles are different, but this will still cause numerical problems. Okay, so you'll have to, well, have some difference here between the two poles that is substantial, otherwise you'll have numerical problems, but in practice this is not really a problem. So I advise you to use place so that you can work also with multivariable systems and you won't have these numerical problems as soon as the state grows, but of course you'll have to choose different poles, which is in practice not such a problem. So here are the responses to the pole placement design in blue, and you have, well, 3 designs with the DLQR method, with R is equal to 0.1, 1 and 10. So obviously here there is a constraint on the control energy that increases, and you can clearly see it on the response, because the closed loop step response, when you go from sign green to red, is slowing down. Okay, well, this is obvious since you're limiting the control energy. In brown here you have the step. Well, when you do a design, you should always look at the control energy, so please do so in your control lab, in your report. Show the designs, but also show the associated control energy, and also put on the plot the saturation values. In this example we have worked without the saturations, but in practice there is always a saturation on the control energy. So again, here you have the example of pole placement and LQR design with an R that is increasing. So when you go from the sign design to the red design, well, you have a limitation on the control energy that is growing, and this is clearly visible here on the curves. So here is a discrete time design, and as said before, well, I expect that there is first, at least if you do pole placement, a continuous time design, and then you take the poles from this continuous time design and transform them in poles for a discrete time design. So the idea is that you take the realization of the original system and that you obtain a discrete time state space representation using the command C to T. If you're not using any argument, then you're using the ZOH method, and this is really important because you want to take into account the zero order hole. So please have a look at the help of C to D for more details. So here, as I've said, the continuous time poles are transformed in discrete time poles for the discrete time design, and this is simply done by the formula exponential of the continuous time poles times TS. This is what is implemented over here, and the place command is exactly the same because you're placing now the poles of AD minus BD K1D. So the place command is used for continuous design and discrete design. Of course, you have to use the corresponding matrices. Once you have K1D, the state feedback, you can compute the feed-forward gain. Beware, this is not the same equation than the one used for continuous design, and this is a source of errors in the control labs. And then of course you can again compute the step responses, and here you have the transfer functions from R to Y and from R to U. So this is pole placement in discrete time, and LQR is very easy. You replace LQR by DLQR. R and Q stay the same. Of course, that Q here, it's C transpose C, but the C in discrete time, it's the output equation, is exactly the same as the one in continuous time design. So R and Q stay the same. Of course, A and D are different, right? So here it's the command DLQR, and again you have this feed forward gain. Same formula as here, but it's a different formula than the one used in continuous time. And of course then you can have a look at the step responses. The step responses are not given in the slide or in this video course, but if you want to run this code, this is really easily done.